Hello, this is Dr. James Camp from Lee College in Baytown, Texas, and welcome to my presentation on numerical types in the C family of languages. Now, before we can understand how the various C languages use their type system, we have to understand how a computer sees a number. So let's say a computer wanted to represent the number 169, just picking that number kind of randomly out of a hat, if you will. It could use the binary representation 10101001. We'll get into why that equals 169 in just a little bit. But first, let's understand the systematization of all this. So each one of these digits is called a bit, and a bit represents a on or off electrical pulse somewhere in the computer's machinery. On would be 1 and off would be 0, and that's why this is what we call binary. You can either have an on or an off, a 1 or a 0, just two possibilities. Now you can group these digits together 8 bits at a time, and 8 bits is equal to 1 byte. And then in a dose of the kind of goofy terminology that computer science is, or at least used to be known for, half a byte, 4 bits, is called a nibble. Isn't that cute? Half a byte is a nibble. Okay. So you have, each byte has a higher order nibble and a lower order nibble, and sometimes those have special meanings. But in this case, we're going to kind of ignore the nibbles and just go with the bytes. Now we could extend this number with more digits. Okay, and when we do this, the result of 16 bits in this case, 2 bytes, is called 1 word. Now word size, the size of a byte has remained fixed since the very beginning of computer science, but the size of a word keeps increasing as machines get faster and bigger, and we would think mostly better. So somewhere in the 1990s or so, words became 32 bits equals 4 bytes. And over the last decade or so, we've evolved into computers that had 64 bits. You've probably heard computers advertised as 64-bit processors, 64-bit operating systems. You may have wondered in installing software on your computer why there are 32-bit versions and 64-bit versions. All has to do with how they compute the size of a word when handling numbers in memory. Okay, a larger word size means you can address more memory. So you can have, a 32-bit system is limited to about 2 gigabytes of memory. A 64-bit system can handle much, much more memory. Okay. So, computers divide numbers into 2 kinds, integers and floating points. An integer can be defined as any positive or negative whole number. So, negative 32, positive 64, negative 101, 3, 2, 7, 5, 9, 32,759. All of these are integers because they are whole numbers. They don't have a decimal point. They don't have any fractional component. Computers, integers are the easiest thing to visualize on a computer. If we take another example of an integer here, 0, 1, 1, 0, 1, 1, 0, 1, say. Okay, each of these bytes, starting at the right and counting toward the left, each bit increases the power of 2. Okay, so this would represent 2 to the 0, which is 1. This would represent 2 to the 1, which would be 2, but since it's a 0, we don't use it. Okay, this is 2 to the second, which is 4. This is 2 to the third, which is 8, and it continues on. 2 to the fourth, 2 to the fifth, which is 32, 2 to the sixth, which is 64, and this would be 2 to the seventh, which would be 128, but again, we're not using it because it's a 0. So we can take 64 plus 32 plus 8 plus 4 plus 1, and we get a value of 109. So the binary number 011011101 is equivalent to the decimal number, base 10, is called decimal 109. How many numbers could we hold in a 8-bit, 1-byte integer? Well, we could get 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 equals 255. So if all ones, we have a max value of 255. But there's a problem. With our 255 place number here, that we haven't left any room for negative numbers. Okay, that this representation, as we've described it so far, has room for 0 to 255, but no negative numbers. The solution is that we still store our number as 0, 1, 1, 0, 1, 1, 0, 1, or whatever other combination of numbers we want. But this first bit gets designated to be the sign bit. Okay, and that means if it's 0, the number is positive. If it's 1, the number is negative. A signed 1-byte. I'm teaching my students about C++. A signed 1-byte integer can hold the values negative 128 to positive 127. You may say, why is it not up to 128 if it's down to negative 128? The answer is we've got 0 in there. So we can go one digit further on the negative direction than on the positive direction. Now, that seems like a pretty limited range. How often do you need to use numbers, especially if we're dealing with engineering calculations that might go higher than 127 or lower than negative 128? So a 2-byte integer, back in the days of 16-bit computers, we used 2-byte integers, and that holds negative 32,768 to positive 32,767. Believe it or not, back when I learned computer science, back in the early 90s, that was an integer, was negative 32,768 to 32,767. The problem with that, of course, is that still there are situations where we need numbers that go significantly higher than that or lower than that. So now that we have 32-bit computers all over the place, and even some 64-bit, it's typical to use a 4-byte integer. And when you use the int type in C++, this is what you're typically going to get these days, is a 4-byte integer which holds negative 2 billion to positive 2 billion. Now, I think you'll agree that that's a pretty useful range. We can get even bigger than that in the 8-byte integer world if we use an entire 64-bit integer, but typically 32-bit is what you're going to get. In C++ compilers in the modern era. Okay, so how do we use these integers in C family languages? We declare an integer using the keyword int. Okay, and so pick a legal name like mynum. Okay. And if we just have int mynum, there's a problem. This does not, in standard C and C++, initialize the value. You would think maybe it would just default to a value of 0, but no. Int mynum will just pick a piece of memory to represent mynum, and whatever value is left in there from the last program that ran that piece of memory is what it gets. So this could leave mynum as, 32,536,000 or something, and you wouldn't know. So C++ gives us, well, the C family gives us a way to initialize these numbers before we use them the first time. So we would say int my other num, can't ever redeclare a variable once we've used it, equals, okay, and then we put in a constant number, negative 21, say. Okay, so that is going to initialize the value to negative 21. We can also use the const keyword in C++ and C#, add that to int, and we get, and we can declare a constant of the universe to be 42, if you're a fan of Douglas Adams. Note that in standard C there is no const keyword, and in Java you use the keyword final instead. I've never figured out why they do that, but that's what they use. And once you use const or final in Java, this value cannot be changed. That's handy for the program because it knows it can store 42 in a pocket of memory that it never has to change. It just has to access it once in a while. Finally, if you're interested in a little bit more range on the positive side, you can make an unsigned int, say my age, and we'll give it the value 32. And we'll put the comment I wish I was still 32. Okay. So those are all various kinds of declarations. We can also use, once we've declared these things, we can use them. We can say my other num plus equals my age. Okay, the plus equals operator takes my age and adds it to the current value of my other num. So I get, so this adds 32 to negative 21 and stores that value in my other num. Okay. We can also set my age equals universe plus my other num. Okay, and that does exactly what you think. It adds, it stores 42 plus whatever this calculation ends up being. 32 minus 21 is 11. Stores that result in my age. Okay, and of course we can always just do plain old assignment statements if we want. My num equals 0. Just stores the number 0 in my num. Okay, so that's how we use integers in C family languages. Know that if we ever tried to assign my num as 0.5 or some sort of number that had a fractional component to it, the compiler would give us an error because ints cannot handle fractional values. So what would we use? So what would we use if we needed a fractional value? We would use a floating point number. What in the world is a floating point number? A floating point number is any number with a fractional part, that is with a decimal point somewhere in the number that floats from place to place. For example, if we took the digits 1, 2, 3, 4, 5, we could float our decimal point here or here or even here, and you'd agree that while we have the same digits, we get three completely different values. 1,234.5 is a much different number than 0.12345. So how do computers see floating points? First off, we need at least 2 bytes to properly represent a floating point number with any reasonable amount of precision. Okay. So we put out our number here, 1,1,0,1,0,1,0,1,0,1. Okay. As before, the first bit is a sign bit. So this is a negative number. So in our representation, that gives us a negative here. Then the next, say, 8 bits represent the base of the number. And you would think we would use the same power of 2 system we used before, but in fact we use fractional powers of 2. So we would get 2, and we count this time left to right. So we'd have 2 to the negative 1 plus 0 plus 2 to the negative 3 plus 0 plus 2 to the negative 1, 2, 3, 4, 5, 2 to the negative 5 plus 2 to the negative 6 plus 2 to the negative 8. Okay, that's our base. Why do we use fractions of a power of 2? I'm honestly not sure why they chose to do it that way, but that's how the people in IEEE set the standard. Okay, and then we have the exponent as a power of 2. So we're going to have this whole thing times 2 to the power of some number here. And the way we represent these, we don't use a sign bit, we just take an integer, but we consider the top half of the integers to be positive and the bottom half of the values to be negative. So we subtract the median value from this. So we have 2 to the 0 is 1, 2 to the second is 4, 1, 2, 0, 1, 2, 3, 4, 2 to the fourth is 16, 2 to the fifth is 32. Okay, and we subtract the median value of this integer, which is about 64. So this would end up being a negative value. We'd have a negative exponent. I'm not going to go through the business of calculating out exactly what this number is, but you can see it's fairly complicated. And you can also hopefully see immediately that there's a problem with this value. We cannot store all fractional numbers exactly because not all fractions are even powers of 2. Okay. For example, uh, 0.1, a really simple, very common fractional number, is a repeating power of 2. Comes out to be something like 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, repeating, kind of like a third is a repeating power of 10 as 0.33333333. Why is this important? So if I take the floating point representation that we had on the previous page, and I write a program that adds 10 cents, $0.10 of allowance for each of my kids each day So if I add 10 cents of allowance each day for a year, 365 days, you would expect that I'd get exactly $36.50, right? The result is not an even $36.50. It's 36.500015. Okay, you can see the computer has made some errors in adding up this number. Now, I think nobody is going to get upset that my children are earning 1/1000th of a cent more each year on this pitiful $36 a year allowance that I'm giving them here. But you can see, I hope, that if you had an engineering calculation that was off by a 1/1000th of a percent like this, that could make a difference if you're calculating tolerances for, say, airplane parts or millionths of an inch tolerances for machinery or computing parts or things. So there is a fix for this. The solution is a 4-byte or 32-bit, and we call it double precision floating point. Okay. And this is precise and accurate to about 15 places after the decimal point. Okay, so my kids would not get an extra 1/1000th of a cent if I were doing my calculations with double precision floating points. And for this reason, I'm going to teach you in my computer science classes never to use float, never to use single precision floating points, always to use double precision. Okay, but I will show you real quick how to declare a float, just in case you ever want to, desperately want to save the memory or something. Okay, so you would say a float my float equals 0.25, and then you put a letter F after it to indicate to the compiler that you really did mean this to be a float and not a double precision floating point. Note two things. One, never use floats. Okay, and two, I chose an even power of 2, okay, which is the case where you can use a float. If you know it's an even power of 2, you can, like 0.25, you can save the memory by using a float. But in our class, we're going to use doubles all the time. So you get a double precision floating point by using the keyword double. Double, my double equals 0.123456789. Okay, and this is, and that gives you enough precision to hold that number. Okay. As before, if you're using C++ or C#, you can use the const keyword to declare a constant. there's a tradition in the C++ community or the C community of using all caps to indicate a constant. So const double pi would equal 3.14159.265, and you could go on if you wanted to. Okay, and again, because I use the keyword const, this value cannot change throughout the program. I don't see why I'd want to change pi, but I can't. As with int, and I think I forgot to show you this in the int page, you can make a calculation in your assignment statement. Double area equals my float squared. So my float times my float times pi. Okay, and those floats will automatically be upgraded to doubles so that they can multiply by the double pi and be stored as the double area. Okay, so I can also, as before with ints, I can just use the variables once I've made them. Now I want area to equal pi times my double squared. I can use the power function, pow, my double to the power of 2. So pi times my double squared, so area of a circle. Okay. So in summary, we have the type int, which is for going to be used for most whole numbers that you use. If you have a whole number, it's better to use an int than a double because of the precision issue. We can use an unsigned int if you really need that extra range in the positive direction. We can use a float, which has very limited precision. So really we do not use floats. And we can use a double, which has better precision. So always use this for engineering calculations. All right. And that's my summary of numerical types in C++. Stay tuned to this channel for more videos on other types in C++ and on other structures in C++ programs. Thank you and have a good day.